Hello everyone, my name is Guoxing Chen and I'm from Shanghai Jiao University. I'm going to present our work, Mutual Attestation for Global Enclaves Without Trusted Third Parties. This is joint work with Professor Yinqian Zhang from Southern University of Science and Technology. As outsourcing storage and computation to clouds become more prevalent, cautious users may raise concerns about whether the cloud could keep their data private and execute their applications as expected. Trusted execution environments, or TEEs, have the potential to offer efficient solutions to these concerns. Examples of TEEs include Intel SGX and AMD SEV, which are available in popular clouds such as Google Cloud, Microsoft Azure, and Alibaba Cloud. A TEE is a secure area of a processor, which is usually called enclave. It protects the confidentiality and integrity of the code and data loaded inside against privileged and unprivileged attackers, such as the operating system. Before interacting with an enclave, the enclave needs to be verified. Thus, a mechanism called remote attestation is introduced. Here, the enclave is denoted as the attester, and the entity that wishes to establish trust on the attester is denoted the verifier. The establishment of trust can be achieved by answering the following three questions. Question 1, is the attester an enclave? The root of trust of the remote attestation procedure lies in some specific component within the processor, such as the root secret, which is bound to the processor's eFuse. This root secret can be used to endorse a particular private key called the attestation key, which is used to sign the report generated by the attester to prove to a verifier that the attester is indeed an enclave running on an authentic TE platform. Hence, when the signed report is verified to be valid, the verifier can be assured that the attester is indeed an enclave. Question 2. What is the attester enclave's identity? One enclave can be identified by the enclave measurement, which is the cryptographic hash of its initial code and data. Usually, the attester enclave's measurement is inserted by the TEE platform into the signed report sent to the verifier, so that the verifier obtains the attester enclave's identity simultaneously when verifying the report. Question 3. Is the identity trusted? Usually, the verifier compares the enclave measurement from the received report with the expected one from some reliable source. So if they are equal, the verifier can be assured that the attester enclave is trusted. In scenarios when the verifier is also an enclave, the trusted enclave's measurement is hard-coded into the verifier enclave's initial data. When TE applications become more complicated and consists of multiple enclaves, these enclaves need to attest each other to establish a trusted relationship before interacting with each other. Such mutual attestation could be achieved when there exist trusted third parties, such as a standalone server, a trusted developer, or a trusted auditor. Each enclave could have the TTPS public key hard-coded into its initial data, and thus can obtain the other's expected measurements from the TTP during runtime. However, including a TTP increases the TCB of the entire application and might also incur extra costs for running public key infrastructures. Therefore, it is often desired to perform mutual attestation without TTPs. However, we found this problem non-trivial. Consider two enclaves A and B. After developing enclave A, its measurement is obtained and can be hard-coded into enclave B's initial data. Then enclave B's measurement is finalized. For A to verify B's identity, it will need to hard-code enclave B's measurement into its initial data. However, this will change its measurement, making the previously hard-coded measurement invalid. Such a circular dependency is the main challenge here. To address this problem, we notice that the measurement calculation is deterministic and sequential. So to compute the measurement of an enclave, the enclave content is first split into fixed length blocks and processed one by one sequentially. A fixed length internal state or intermediate hash is first initialized and then updated after each block is processed. So after updating the last block, a finalization function outputs the final hash, which is the enclave measurement. A key observation here is that if we know the intermediate hash and the information to perform specific measuring operations, and it would be sufficient to derive the final output. So here comes our solution, MAGE. The idea is to introduce a common part at the end of each enclave to store the intermediate states of the enclave's measuring process right before the final step. These intermediate hashes reflect the specific parts of each enclave. Due to this common part, this enclave's measurements will be changed as follows. During enclave creation, the measurement calculation before this common part remains the same. And it will continue to update the content of the common part and then finalize the measurements. Now I'll describe how the measurements could be obtained during runtime. So each enclave with the common part could derive the other enclave's measurements. Particularly, the corresponding intermediate hashes are retrieved from the common part. And then the enclave could continue updating the intermediate hashes with the contents of the common part and finalize the measurement. We provide a prototype implementation of MAGE for Intel SGX by extending the Intel SGX SDK. Specifically, it consists of 3 components. The first is a MAGE library. When included, it will reserve a read-only data section named SGX MAGE to store the intermediate hashes. It also provides APIs for deriving measurements from this section. Secondly, we modify the enclave loader to load the MAGE section after all enclave code and data. So it will first follow the original loading process, except that when SGX MAGE section is encountered, it will be skipped. So after all others are loaded, the modified enclave loader will load pages in the MAGE section. Thirdly, we modify the signing tool to provide the following 2 functionalities. Given an enclave, the modified signing tool simulates the loading process, except for the MAGE section, and extracts the intermediate hash. Then, after collecting the intermediate hashes of all trusted enclaves, the modified signing tools injects them into the MAGE section of each enclave. Next, I'll describe the performance evaluation of our prototype implementation. So for the memory overhead, it is linear with the number of trusted enclaves. Particularly, 48 bytes are needed to store the auxiliary information, such as the intermediate hash and the page metadata for deriving one enclave measurement. So a 4K page could support up to 85 enclaves. As for the measurement derivation efficiency, it is also linear with the size of the MAGE section. And in our evaluation, it takes roughly 21.7 microseconds to derive one measurement when the MAGE section contains only 1 page. In the paper, we also discussed alternative designs such as extending MAGE with untrusted storage for better scalability. We discussed the potential extensions to other TEs or even between different types of TEs. Certainly, we also discussed supporting enclave updates and private code. Please refer to the paper for more details. That's all for my talk. Thanks for listening.